Problem number 7. Two satellites are initially in identical circular orbits around the Sun, with orbital speed v equal 10⁴ meters per second. The first satellite fires its thrusters toward the Sun and quickly obtain a radial velocity delta Vr equal 1 meter per second. The second satellite instead fires its thruster behind it and quickly increases its tangential velocity by delta Vt. If the two satellites subsequently perform orbits with the same period, approximately what was delta Vt? Solution for problem number 7. By Kepler's third law, the period only depends on a semi-major axis A, because t square proportional to a cube. However, the total energy of an elliptical orbit is determined by the semi-major axis E equal negative gmm over 2a. Hence, the two satellites must have the same energy and hence the same final speed, because they have in this point the same potential energy. So we have v plus v delta v tangential square equal v square plus delta vr square. And from here we can count what is delta Vt. That will be this expression, which is approximately this one, because delta Vr much less than V. And finally, when we put numbers, we will get this much. So that's the answer A, and that was solution for problem number 7. Problem number 8. A conveyor belt is moving with the velocity v to the east. A block with velocity v to the south slides from the ground onto the conveyor belt. The coefficient of friction between the block and the belt is μ. The block stops slipping after a time. Next one. Solution for problem number 8. Relative velocity of the block compared to conveyor belt is square root from 2 multiplied by v. Acceleration due to friction equal μg. Total time to stop for this block compared to belt is initial speed divided by acceleration, which is square root from 2v over μg. That's answer C, and that was a solution for problem number 8. Problem number 9. Two equal masses m are connected by an elastic string that acts like an ideal spring with the spring constant k and the unstretched length L. The two masses are hung over a frictionless pulley. What is the total length of the string at equilibrium? Diagram not necessarily to scale. Solution for problem number 9. Balancing the string tension with the gravitational force on either of the masses give us kx equal mg, where x is enlargement. From here we can find that total length of this string in equilibrium equal L plus x, which is L plus mg over k. That was answer B, and that was solution for problem number 9. Problem number 10. The two masses are both displaced downward by a small vertical distance x and simultaneously released from rest. What is the period of oscillations? Solution for problem number 10. Gravity does not affect the oscillation frequency because it was compensated by initial stretch of this string. And now when its both masses oscillate, the midpoint of this string is not moving. It means that we can think about this oscillation as a simultaneous oscillation of two masses relative to this midpoint. It means that one mass oscillates on half of spring, which has effective spring constant 2k. So it means that solution for period will be 2 pi multiplied by square root from m over 2k, or pi multiplied by square root from 2m over k, which is answer B, and that was solution for problem number 10.